So let me remind you what we did last time. Last time we started solving Schrödinger equation, and we solved a particle in a box problem. So the potential was U of x, which you also solved in the exam, was equal to 0 if x is inside a box. Let me call this L, and infinity otherwise. And we draw this like that. Right. So this is U of x, this is x. So U is equal to 0 here, infinity here, and infinity here, and this is x is equal to 0, this is x is equal to a. And we found the solutions, like psi, we found them to be indexed with some quantum number n, and they were like 2 over L sine n pi over L times x. And the corresponding eigenvalues, so E n was equal to h bar squared pi squared 2m L squared times n squared. So this 2 over L is normalization constant, which comes from like this dx. If you integrate from minus infinity to plus infinity, there is nothing outside the box, so you can actually integrate from 0 to a. And psi for any n of x is 1. And since these are like sine squared kx, this integral can be taken. So that's the normalization. So one thing that we need to be aware is like, so we can choose the solutions to be real for one-dimensional case, but we can also like choose it to be any other phase. Suppose psi n of x is a solution, and not to write the whole thing again and again, let me define an operator x, which is minus h bar squared over 2m d squared dx squared plus u of x, right? This is acting on, and it is like saying that this depends on x this way. And if this psi n is a solution, like h of x, psi n of x is equal to en psi n of x. But I can like insert like a phase here, like e to the I theta and e to the I theta. Basically, I can multiply the whole equation with e to the I theta, and I can introduce like this psi tilde n is equal to e to the I theta psi n of x. These are functions of x. Okay, so like that. So this is also x. Then this little algebra proves this psi tilde n is also an eigenstate. Okay. So what we are saying is like Schrödinger equation is a differential equation, but this differential equation is actually, when it's written and solved, turns out to be an eigenvalue equation. And an eigenvalue equation has two unknowns. These are eigenfunctions, right? Eigenfunctions of the solution, and also eigenvalues. So we solve them at the same time. Good. And for any given eigenfunction, I can multiply it with some arbitrary phase, and I have also a solution. Simple stuff. And okay, so let's consider observables, and the simplest observable was the probability. And let's define P of x1 and x2, which is probability to find the particle between x1 and x2. And I can just write it from like this, integrate from x1 to x2 dx psi of x squared, right? And these are also like, okay, what is this? This is x1 to x2 dx 2 over L. When I take the square, I have this 2 over L from normalization. And this is sine squared. Let me write Kn to be brief, x. And we can also integrate this, right? This is how you integrate it in the exam. This is something like what? It is like 1 over L x from x1 to x2 minus 1 over L sine 2 Kn x. Why 2? Because I have to convert sine square to sine and cosine without square. And for that, that's why it is 2 divided by 2 Kn x1 and x2. And that's going to give you these graphs which we plotted, right? Just the area under given x1 and x2. So let's we can consider expectation values of operators. Huh? What's that? Yes, but sine square, you convert it to cosine, right? Because I don't know how to integrate sine square, but if you convert it to sine and cosine without square, there has to be cosine, and the integral of cosine is going to be sine, right? This is correct. Yeah, I think this is correct. So expectation values of operators. For example, we can think about the expectation value of x, and we can also integrate from 0 to a dx psi n of x. There's actually a star, but in our case, we chose this arbitrary phase to be 1, so I don't actually need to put the complex conjugate. So this is x, and this is psi n of x. So this is a little bit more complicated integral, but not a big deal. We can use exactly the same trick, right? This is sine, this is sine, and sine square, we have to first do by parts to eliminate this. Yada, right? You know, everybody knows how to take integrals. And what you are going to find, okay, here is exercise for you. Let me say optional homework. So this is going to be L over 2. So let's calculate P similarly. P, I'm going to write exactly the same thing. And I'll replace this x with minus I h bar del x. Yes. Yes. But since we took reals, I mean, to be safe, you can always put complex conjugate, but complex conjugate of a real function is itself. Yeah. And when you do this, right, this is, let's write this. This is 2 over L sine Kn x minus I h bar del x. This is like this. This is sine Kn x, and derivative of sine is going to be cosine, and it is going to bring Kn, right? Did I get that right? Yes, right? And now I look at this function. Let's see what this is. Exactly, right? This is going to be 1 over L sine 2kl, but integral of sine 2kl is going to be cosine 2kn x over 2kn, and you take it from 0 to L. And let's write what this is. This is 1 over L cosine 2n pi over L x divided by 2n pi over L. from 0 to L. If I put L, this is 2, cosine 2 pi n is 1, minus, if I put 0, cosine 0 is 1, 1 minus 1 is 0. Right? Oh, yes, yes, there is like A here, right? This should be L. Yeah, thank you. Is there another one? So this, yeah, this one should also be L. Good, thank you. So this makes sense since particle is trapped inside the box, right? Expectation value of momentum is 0. So basically it doesn't go anywhere. If there was like a finite non-zero momentum, that would mean particle is moving. But if it's in like a box, it cannot move. Every time it moves, it's going to bounce off the walls, and average will be 0. 0 expected momentum. So, however, we can like decompose, for example, this function sine knx. We can decompose it into e to the I knx minus e to the minus I knx. And this first piece, we call this right moving wave, right mover. This one is a left mover. And if I take, rather than this whole function, only take this and act on momentum, and I can define an eigenvalue equation, just like the eigenvalue equation I defined in the Schrödinger equation. I can say, let's look at this p e to the I knx, and this p is what? It is minus I h bar del del x e to the I kn, and this is going to give me h bar kn e to the I kn. So this is x, this is also x. So the sign is not an exact eigenfunction of momentum operator, right? But this e to the ik or e to the minus ik are exact eigenfunctions of the momentum operator. But since momentum is not conserved in the box, eigenfunctions of momentum and eigenfunctions of Hamiltonian, which is the particle in a box, are distinct. They are not the same. So all of these observations we are coming to from the solution of the simplest problem, which is particle in a box, but they are valid in arbitrary problems, right? These are like valid in quantum mechanics in general. But since we solve this problem and we have these results, we can derive all of these, or we can see all of these results for ourselves easily. Yeah, the moment it's like a because walls are infinitely strong, it is an elastic collision, right? And the magnitude will be the same, but the direction will change. Yes. So another observation is so-called orthogonality. So we saw that the normalization is like this, right? The x psi n of x, there's like star, but we can forget star, at least for this problem. And the question is, what if I take these indices different? Like suppose this one is m, and this one is n. And we can also look at that. So this is going to be, so now we don't know what this is. So this is going to be equal to dx 2 over L sine n pi over Lx, and the same thing with m. And for this I want to use this sine alpha, sine beta is equal to 1/2 cosine alpha minus beta over 2 plus cosine alpha plus beta over 2. Then this integral is going to be 2 over L times 1/2, this 1/2. And now I can take this integral, integral of cosine is sine, so this is sine n minus m pi over Lx, and divide this entire thing by n minus m over L pi, and the same thing, plus, plus, and plus, and put the boundaries from 0 to L, right? And if I put L, this is like sine n minus m, right? Like, let me just show one. This is sine n minus m over L, and x is equal to L. So these are, okay, there's also pi. So this is L. What is that? This is 0. And if I put L is equal to 0, this is sine 0, this is 0. And basically this is 0, and this is also 0. This entire thing is going to be 0. So this is assuming n is not equal to m. If n was equal to m, I wouldn't be able to do that because I would be dividing with 0. But if n is equal to m, I know it is from the normalization, right? It is exactly the same thing. So I can write this thing as like as this. So this thing is equal to 1 if n is equal to m, 0 otherwise. And there is like a nice way to show this. We generally show this with delta nm, and this is what we call Dirac delta. Yes, like there are like for some problems, yeah, that is what it is. But in our problem, so this is my Dirac delta. This is how I define it, right? And in my case, when n is equal to m, it is not going to infinity, it's going to 1. It's like a discrete Dirac delta if you want. For continuum Dirac delta, yes, you need to take it to infinity because you need to use it inside integrals to cancel the integrals. And from this, we can show something called completeness. Completeness. So any function, so psi of x, so this is like an arbitrary function. Any function can be written in terms of these functions I found, Cn, psi n of x. And how do I prove this? I can just multiply both sides with, okay, multiply both sides with psi m star x and integrate. So let's do that. So I'll just take this guy. So this is dx. This is psi m star. And I'll do exactly the same thing here. So let me push this just a little bit. So dx psi m star of x. But we just show this, right? We just show this delta m n, and inside this summation, right? So this is like whenever like I am summing over all possible n's, right? C1, C2, C3, and whenever my n is equal to m, I pick it up. Otherwise, all the other ones are 0. So this immediately is going to give me Cm. Right? That's a nice thing about the Dirac delta function. Then, by writing this, we can, I mean, this is not the proof, but we can like convince ourselves that we can write any function in terms of psi n of x. And I think some people know this from like a theorem in mathematics. Does anybody know what this means? We are expanding a function, an arbitrary function, in terms of sines and cosines. Yeah, this is the Fourier series, right? Like if you want, these are like Fourier coefficients. So last comment is let's consider time dependent form. So suppose I have this psi of x is equal to some alpha. Let's take the first two, psi 1 of x, and so this is like this sign with n is equal to 1 plus beta psi 2 of x. And I know h psi 1 is going to be equal to E1 psi 1, and h psi 2 is going to be equal to E2 psi 2. If you want, like, so I choose the function to be not the exact eigenstate, but like a linear combination of two exact eigenstates. Now I want to see, oh, maybe like this is like a common mistake. Time independent Schrödinger equation is linear, so if psi 1 and psi 2 solves, their linear combination should also solve. And what people do is like h alpha psi 1 x plus beta psi 2 of x. And you can open this up, right? This is alpha E1 psi 1 of x plus beta E2 psi 2 of x. So does this satisfy the condition for exact eigenvalue equation? Right? So we expect something like some overall eigenvalue, if you want, lambda times exactly what we feed in. And what we feed in is this object. Maybe I can write it like that. So we expect this. So do you think this is an eigenvalue, exact eigenstate of Hamiltonian? The question. So this is beta. So this psi, let me use uppercase psi. The question is, given psi 1 and psi 2, lowercase psi's eigenfunctions of Hamiltonian, which is shown here, can I say that the linear combination of them, which is alpha psi 1 plus beta psi 2, can I say that it is also eigenfunction based on this, by just looking at these two lines? Should I pick somebody and ask? So is this uppercase psi, which is formed from two eigenstates, two exact eigenfunctions, is this also an eigenfunction of Hamiltonian, time-independent Hamiltonian? Is that clear? Yes? How many people say yes? How many people say no? The answer is no, right? I mean, I don't have like something like some E, overall E times the function. Like I need to have something times psi of x, but I don't have that, right? I think here, these are E1. Of course, if these two states had exactly the same eigenvalue, I would just pull the E1 and E2, which is equal, out, and I would say they are identical, but they are not. So in general, psi is not the eigenfunction of time-independent Schrödinger equation. Then where is the linearity, right? Why do we say the Schrödinger equation is linear? To see that I can consider time-dependent Schrödinger equation, I h bar del t psi is equal to h psi, but now this is going to be x and t, and this is going to be x and t, and I need to like take this ansatz here and find its time-dependent version, but it is easy to do because we already solved the equation and we found e to the minus I E1 over h bar t, and the second one is e to the minus I E2 over h bar t. And here's a little exercise for you, again, optional homework. homework. Substitute this psi of x comma t in time-dependent Schrodinger equation and see that it is a solution. Yeah, these, like I said, like, you know, all of these are derived from like simple particle in a box problem, but they are valid for arbitrary, like they are the property of quantum mechanics and Hilbert space, right? But if you can understand it for this problem, you basically understand it for all other problems. So let's consider another problem, so-called, and this is part of the homework, right? So your job is to figure out, like if you remember, here's the hint. We said the full solution was equal to, like it was separable, and it was like purely x-dependent part and purely t-dependent part. And this was always trivial, right? We found that part. By using this, we can go back and write down psi x comma t. So that's what I did here. Okay. Any comments, questions? Okay.
What is Hilbert space?
Like Hilbert space is like this vector space. The space we live in right now is the vector space, right? There's like x direction, y direction, and z direction. And I can define mathematics on that. I can like do like these inner products, right? I can take vectors and do inner products. In quantum mechanics, there's also a space like that, but that space is not this trivial three-dimensional space we live in. It is first, it is an infinite dimensional space, because these ends go from minus infinity to these ends go from 1 to infinity. There are infinitely many eigenfunctions, and you can think about these eigenfunctions to be the unit vectors in Hilbert space, exactly like x, y, z are unit vectors in three-dimensional space. And you can think about this to be like inner product in this Hilbert space, right? Like think about Ex and Ey, right? This is 0, but if Ex and Ex, if I take them to be in the same direction, this is 1. So this is exactly the same identity. So the inner product definition is changed. Some other properties of the space is changed. For example, the functions we require are square integrable. They have to have some nice properties, and there are some axioms that actually doesn't matter. This is called Hilbert space. So in quantum mechanics, we go from like this three-dimensional trivial space to Hilbert space. And these are the rules, and all of these things I show you are the properties of this Hilbert space. All right, I want to introduce one more problem. Maybe I may not solve all of it, but we can at least talk about it until the break. Another classic is finite potential well. So the walls were infinite, right? And in real life, there are no infinities in real life. So let's consider the case of finite walls. So again, a box, but finite walls. And what this means is, here's my coordinate system, if you want. So I want to have my x and y. And this is my u of x. And let me just choose my coordinate in a nice manner. Like this is like x is equal to 0. And I have, let me write a because L is a little bit harder to write. So this is minus a over 2. And this is maybe a little bit here. Okay, this is 2. So this is a over 2. And if I am inside the box, v is again 0. But if I'm outside the box, I have these finite walls. So this is, let's call this some u0 constant. But before solving this problem, maybe we can think about the symmetries of this problem, right? Like the problem we are trying to solve is the Schrödinger equation, and we put it in a form like this, like hx times psi of x is equal to e times psi of x. This is what we want to solve, and h, if you want, I put it in operator form, but I sometimes don't put the head because we know what it is. This is minus h bar squared over 2m d squared dx squared plus u of x. So what I can do about this is, like, suppose I have this equation, or like suppose like you want to pull a prank on your friend, and you go and change his or her papers and put wherever he or she writes x, you put minus x, right? At the end of the day, x is a label. Whenever I see x, I can write minus x, and that works, right? Nothing changed. Is there any problem, right? Like, I have a right-hand side and left-hand side, put minus x everywhere. However, I go back and look at my potential. So I look at here, and this shows me u of x is actually equal to u of minus x, right? Also, I look at the derivative operator. This is dx squared, and taking derivative with respect to x and minus x is the same thing, or we can show it like this, d minus x squared, right? This is if you want a change of variable, and every d dx comes with like a overall minus 1, and if you do it twice, it is 1, right? Is that clear? So what this little argument shows is h of x is equal to h of minus x. Then I can take this equation and make this minus x plus x, because that's my that's the symmetry of the problem I have. That's the property of the Hamiltonian. Now I look at this line, and I look at this line, right? So this shows, so this psi here and this psi are indistinguishable. Like if your friend solved this for this psi and you bring it to this psi, nobody would notice it, right? This is exactly the same problem. But earlier in the beginning, we showed wave function is defined up to an arbitrary constant, right, which was phase. So this shows psi of minus x can be psi of x, but there is like an arbitrary phase, right? We like mentioned in the beginning. So there is nothing that prevents me from putting this e to the I theta. Good. Now you come to here and say, okay, if I do this one time, maybe I can do it one more time, right? Wherever I see psi of minus x, let me copy this and do it one more time. Whenever I see psi x, I will put minus psi x, but minus minus is going to be plus, and this will be minus. But I have an expression for minus here, right? I'll substitute this. There is e to the I theta, e to the I theta, and psi of x. But now you can see, so this right-hand side and left-hand side, they have exactly the same psi. Then what can I say about this theta? So then e to the I theta plus e to the I theta is e to the I 2 theta should be what? 1, right? And if this is 1, 2 theta can be either 0 or 2 pi. right? 2 pi is also fine. Then theta is equal to 0 or pi. Now I go back to this thing I said. I said psi of minus x was equal to e to the I theta psi of x. And there are two possibilities. If theta is equal to 0, psi of minus x is equal to psi of x. And if theta is equal to pi, psi of x is equal to psi of minus x is equal to minus psi of x. So these are so-called even functions. And these are odd functions. Right? So all eigenfunctions of this Schrödinger equation, they have to satisfy this condition. So then I can say, okay, rather than doing this for like even and odd at the same time, I can first consider even and solve it. Once I'm done, I can consider odd and solve it. And maybe we can take a break here, and then in the second hour, I can show you how much simplification this will bring us in the equations.